In this presentation, we'll look at how Hyperlink supports the complete process of serial link design and verification. Hyperlinks is an integrated family of products for high-speed system design, automated optimization, and verification. By design, we mean all the planning and analysis that you do before layout to define the rules you want to use to place and route the board. By optimization, we mean using automated tools to improve design performance for a metric of interest. You can certainly use an interactive design capture, analyze, review loop to improve your design, but that takes too long. We'll look at how hyperlinks can help you improve design performance automatically. By verification, we mean post-layout analysis, or what you do once the board is routed to determine that the design is ready to release to fabrication. There are two main design application areas for hyperlinks: serial link design and verification, which we're talking about here, DDR interface design and verification, and general purpose signal and power integrity, which overlap with some of the capabilities we'll discuss here. Hyperlink's products include Hyperlink schematic analysis, which automates parametric checks, eliminating the necessity to manually review complex schematics. Hyperlink's AMS, a powerful circuit simulator for analyzing complex analog and mixed signals. Hyperlink's DRC, which provides fast, rules-based design checking of PCB layouts. Hyperlink's DRC can identify layout issues in a fraction of the time that simulation requires. And screening designs with DRC before investing in detailed modeling and simulation will help you speed your design cycle. Hyperlink's Advanced Solvers, which provides accurate 3D electromagnetic modeling of PCB structures, and are seamlessly integrated with Hyperlink's SI and PI to provide complete front-to-back analysis flows. Hyperlink's SI and PI, which share a common user interface. Hyperlink's SI performs signal integrity analysis of DDR interfaces, SerDes-based serial channels, and general-purpose high-speed design. Hyperlink's PI performs DC and AC analysis of PCB power delivery networks, or PDNs. Hyperlinks is tightly integrated with Siemens' family of PCB design capture and layout tools. Design is an iterative process. As you lay out a board, using analysis during the physical design cycle can help you tune and improve the design in real time, rather than waiting until layout is complete, when it's too late to make substantive changes. Combining hyperlinks with Siemens design capture and layout can significantly reduce your design cycle and improve your design's performance. In this presentation, we'll focus on analyzing serial links for standards protocol compliance with hyperlinks. Serial protocol standards outline specific requirements that must be met for a link to be considered compliant with the standard, and the methodologies used to assess them. Compliance with these requirements is necessary in order for a board to work properly. Some common protocols are HDMI, USB, Ethernet, and PCI Express, among others. Hyperlinks has built-in support for over 200 popular protocols and variants for easy automated compliance analysis. We'll dive more into that during this presentation. A typical hyperlink SerDes analysis flow involves pre-layout analysis, PCB layout, design optimization, and post-layout verification of the completed design. Pre-layout analysis begins with a stack-up study that defines the materials and thickness that will be used to construct the board. Pad stacks and vias are defined, then used to create channel models that represent how signals will be routed. These channel models are used to drive topology exploration, evaluating layout alternatives, and introducing additional design features by adding one discontinuity at a time. Automated protocol compliance analysis is used to evaluate the channel model and assess it for operating margin. During PCB layout, layout rules determined during pre-layout analysis are implemented. You can use hyperlinks with any layout tool, but it works better with Siemens Expedition because it's integrated. Complex VIA support in Expedition Layout lets SI, PI, and PCB design specialists work closely together and stay in sync. Expedition shares the same StackUp editor from Hyperlinks to easily implement the StackUp and routing constraints defined by Hyperlinks and the SI/PI expert. Post layout verification with BoardSim uses Hyperlink's unique progressive verification methodology to find as many potential layout issues as possible, as quickly as possible, with as little effort as possible. First, Hyperlink's DRC automates traditional manual design reviews, replacing tedious visual inspection with fast, automated analysis. Next, compliance analysis verifies each and every serial link for compliance with the associated protocol standard. Finally, IBIS AMI simulation can be used to predict system operation margins with the actual SerDes IP and device programming. With other signal and power integrity flows, expert users must acquire analysis tools from different companies, then figure out how to put them together to create a flow. Users need to figure out how to pass data between the tools, including how that data needs to be named and formatted. It's a lot of work, and the process needs to be requalified whenever any one of those analysis tools changes in any way, because that might impact the overall process and the quality of the results. With hyperlinks, the different tools are already integrated, with reference analysis flows defined and proven right out of the box. This presentation will discuss how the SerDes flow covers the full range of analysis: pre-layout design exploration and physical layout guideline development, automated design optimization, and full system post-layout verification for serial channels. Let's start with pre-layout serial link design. Pre-layout analysis explores options with cost, size, density, and performance of the PCB. For serial links, we first create a design stackup and then experiment with trace and via design options to explore topologies with Hyperlinks LineSim. This process is interactive and graphical, allowing users to capture, simulate, review, and modify the design as time allows. The output will be shared with the layout group for implementation. Integration between Siemens Expedition and Hyperlinks will make that communication easiest, but Hyperlinks can work with any layout flow. Pre-layout design exploration is an inherently iterative process for both power and signal integrity. We define and refine elements of the design in stages, starting with the foundational element like the design stackup, and ending up with specific details like topologies, routing segment lengths, and tolerances. We'll explore two types of pre-layout flows: a power integrity flow, which starts with stackup design and then includes DC and AC power integrity. In some cases, DC and power integrity are additive. The power degradation at the IC is the sum of the two, so we need to adopt a budgeting strategy for how much voltage we can afford to lose for each impairment. In other cases, they're relatively independent, so our budgets can be more relaxed. The signal integrity flow also starts with stackup design. Create your pad stacks and then move on to the design of traces and vias, the building blocks of the interconnect. Then into exploring routing topologies and exploring your driver strength and termination. Hyperlinks helps users develop a stackup that accurately represents what they will get from the manufacturer. It doesn't make sense to spend a lot of time simulating something that doesn't accurately represent what you plan to build. With Hyperlinks, you can design around a Z-knot and see what changes affect your Z-knot per layer. You can include manufacturer options like surface roughness and trapezoidal traces for more accuracy. There is an extensive list of options and customizations that you can do to the stackup that use real-world values. While not a dedicated stackup design tool, Siemens EDA does offer a dedicated stackup design tool that easily integrates with Hyperlinks. Z-Planner has an extensive library of materials and options created from close collaboration with manufacturers. There are two stages to power delivery network design: steady state or DC drop analysis, and AC or decoupling analysis. DC drop analysis analyzes current flow and voltage drop in the design based on maximum DC conditions. We look for voltage drops and current densities that exceed allowable limits, then adjust the layout to correct any problems we find. Hyperlinks allows us to import component and plane data from PCB layouts in progress and analyze them to look for issues. The LineSim schematic editor is a hybrid editor. It can capture a model for a signal topology, a power plane layout, or the combination of both. In this case, LineSim allows us to load the power plane and make quick what-if adjustments, then rerun analysis to test different fixes for power delivery issues. Device switching behavior creates AC power supply noise on the system's power rails. When the VRM uses a remote sense line, DC drop at the component input is kept to minimal levels, and DC and AC analysis can be considered separately. When the VRM does not have a sense line, the AC power supply noise is superimposed on any voltage drop that may already exist, and the effects of both AC and DC behavior should be considered together. The observed AC noise will vary with frequency, depending on the decoupling capacitors used, their quantity and location, and how they are connected to their respective power planes. PDN impedance is a complex, distributed problem best suited to analysis with electromagnetic solvers. Hyperlinks offers pre-layout decoupling analysis flows comparable to that for DC analysis. The PDN can be extracted from a design currently in active layout, modeled and analyzed, then exported to the PDN editor in LineSim for interactive what-if analysis to explore possible improvements in the design. The pre-layout design flow starts with a stack-up study and definition using Z-Planner. Different materials and arrangements are considered to achieve design goals. Next, we use LineSim to create pad stacks, vias, and a channel topology. We can use swept parameter analysis to optimize trace geometries and spacing for our serial links. LineSim can capture and model the full electrical channel across multiple boards. We start with a simple channel model and add detail as we progress. There's no point spending a lot of time creating detailed models if we have basic problems with the length of the interconnect. We start with 2D via models and get a rough idea if we are passing or not, then create more detailed models as we refine the design. Then, we will run the SerDes compliant check wizard to assess the channel's compliance with the standard and predicted operating margin. The margins we see during pre-layout analysis will be compared to the simulations we performed during post-layout stage to see if the post-layout results match our pre-layout expectations. Some items we need when defining our electrical channels are the schematic elements, S parameters, and a full wave solver. The goal is to capture the channel model as we intend to route it. We introduce complexity gradually into the design as we continue to simulate it in a process we call progressive accuracy. We start with 2D via models, then add 3D models of vias and breakout areas as we go. We have access to the Hyperlinks 3D field solver, which is fully integrated with LineSim. How does compliance analysis compare to IBIS AMI simulation, and why is it useful? Compliance analysis focuses on the channel itself without vendor-specific IP. That means compliance analysis can always be run even when no IBIS AMI models are available. The analysis ensures the channel meets the requirements laid out in the corresponding protocol spec. Hyperlinks compliance analysis produces a detailed report of which channels passed, which channels failed, and by how much, so you'll know exactly where to focus your efforts. Hyperlink supports protocol-specific analysis for over 200 different protocols and variants, providing the broadest standards-based support in the industry. The CertiS Compliance Check Wizard provides comprehensive results reporting, including compliance requirement versus measured values, equalization settings, time domain and frequency domain plots, as well as links to waveforms and eye diagrams. The report provides additional information on driver and receiver pins for each net, as well as the ability to generate PDF reports. Most importantly, you know which nets passed, which nets failed, and by how much. Now let's talk about automating and optimizing your design. During pre-layout serial link simulation, 3D Explorer and S-parameter analysis is commonly used when exploring schematic topologies. We also use independent tools such as Design Space Explorer to perform more intensive optimization of specific structures like breakout vias. We'll explore that next. 3D Explorer is a template-driven 3D area modeling tool that is part of the Hyperlinks Advanced Solvers product. It allows the user to create, view, and analyze 3D structures. For example, a DC blocking capacitor structure. This allows common PCB structures to be modeled and analyzed using swept parameter analysis. 3D Explorer creates projects that are sent to one of the three solvers, Fast3D, Hybrid, or Full Wave, for analysis. Then the results are analyzed to extract key figures of merit. 3D Explorer generates reports that show what design parameters are swept, and with their values and corresponding figures of merit for each case analyzed. This allows users to see how design performance varies with each parameter and to pick the best combination of design parameters for their application. Let's focus on a major area for CertiS design optimization, the integration of 3D Explorer and Design Space Explorer, or DSE, with Expedition Layout for complex via design. Hyperlink's 3D Explorer allows use of swept parameter analysis to explore a via design, but practical performance constraints limit that to design spaces with a few dozen permutations. Hyperlink's Design Space Explorer extends the size of the explorable design space to millions of permutations. Hyperlink's DSE is based on Siemens HEEDS technology, which efficiently searches and characterizes very large design spaces to perform fully automated multi-objective optimization on 3D structures such as complex vias. Hyperlink's integration with Expedition means that an optimized structure can be easily sent to Expedition and repeated throughout the design. Vias and component breakouts comprise only a small fraction of a net's overall length, but they account for most of the reflections and crosstalk that impair signal quality. If you consider the dimensional parameters that you can vary during design, there are tens of thousands of possible design permutations, far too many to consider individually. Hyperlink's DSE lets you define key performance metrics that you want to optimize, and then explore huge design spaces quickly to find the best trade-offs for your design. It's ideally suited for optimizing recurring structures like vias and component breakouts. Hyperlink's DSE uses a unique Sherpa algorithm that allows you to find workable solutions quickly and then continue to improve performance by running additional experiments. Have a design space of 1 million permutations or more? No problem. Sherpa can efficiently balance goal optimization against avoiding local minima and maxima, often providing workable results with a budget of as little as 100 experiments. The Siemens integrated flow allows users to create complex vias in Expedition Layout that can be imported for analysis and optimization, then exported back to Expedition and used as a recurring structure in the design. The structure to be optimized and replicated is originally created in Expedition Layout. Hyperlinks can then be used to optimize impedance, insertion and return loss by changing different elements of the structure, with the optimized design sent back to layout. The resulting complex vias can be saved in the library for later reuse on boards that have the same fundamental characteristics or used as a starting point for subsequent designs.
Thanks for being here today. I want to talk about post layout serial link verification in Hyperlinks SI. Post layout verification is traditionally performed at the end of the PCB design cycle, right before fabrication. Sometimes, this is the only analysis engineers perform if they don't have tools or expertise to run pre layout design exploration or design optimization themselves. Often, there's a rush to get the design out to fabrication once the board is routed, and experts have only limited time to select a group of signals or objects. Hyperlinks provides an automated flow that lets users analyze every serial link on the design, not just the corner cases. In our methodology, we start by running electrical design rule checks during layout to look for common problems. Then we're going to use standards compliance analysis to look at the system level interconnect and make sure it meets protocol requirements. And finally, only once we've gotten as many problems off the table as possible, we'll use IBIS AMI or vendor based model simulation to predict how the system will perform with actual devices and settings. We call this methodology progressive verification. It allows us to find layout problems as early in the design cycle as possible with as little effort as possible. We deliberately separate verification into different stages so that we can defer time consuming and expertise intensive analysis, allowing us to make the best use of scarce SI experts. We start with simple analysis and then add accuracy in controlled stages because the time needed to model and analyze the system increases as we make the analysis more accurate. And that's true with any tool, not just hyperlinks. The time and expertise needed to perform simulation increases dramatically as analysis accuracy goes up. As we mentioned, electrical rule checks automate manual inspection, finding problems in seconds or minutes that would take hours or days to find using modeling and simulation. These checks cover a wide variety of power and signal integrity issues. Traces crossing gaps in planes are a good example of problems that can be found quickly. A DRC analysis can process hundreds of signals per second, identifying exactly which signals have problems and where. Finding a trace crossing a split using simulation is problematic. The modeling and simulation are time consuming. The actual effect on signal quality may be relatively small, and isolating the exact location of the problem from simulation results can be difficult. Hyperlink's DRC performs analog, EMI, PI, SI, and electrical safety checks in a fraction of the time it takes to perform those same checks manually, producing detailed reports that show exactly where and how each violation occurred. It also produces reports that can be given to PCB designers to quickly locate and correct each problem. Hyperlinks uses the DRC engine to find the areas on the board that require 3D modeling. The signal and its associated return path are fully modeled, and the area boundaries are chosen to ensure TEM flow at the signal ports. Hyperlinks automatically creates the corresponding simulation projects for the 3D full wave solver, ready to be solved in a batch analysis. Now let's move on to running this analysis with 3D VIA models. When people simulate a routed net using 3D VIAs, they typically model the net in three stages. First, they identify the areas of the net that require 3D models. Next, they cut those areas out of the board, create 3D projects, and solve them using a full wave solver. Finally, then assemble the net topology in a schematic editor by stitching the solved areas together with transmission line, connector, and component package model. The methodology is called cut and stitch modeling, and doing it by hand is difficult, time consuming, and error prone. That's what most people do. Using manual post route extraction means that you won't be able to verify all of the nets in your system because that will require too much effort. Typically, only a handful of nets get modeled and verified. Usually, it's the longest, shortest nets that have unusual routing and a few random samples. This is what a typical post route analysis might cover. Anything that doesn't get verified, well, that's just going back to our hope for the best strategy, isn't it? Hyperlinks will let you verify all of the nets in your design automatically. You can reduce design risk by using hyperlinks to find those odd layout issues that theoretically shouldn't cause a problem but often do. Anytime you can find and correct a layout problem before prototype fabrication, that's a lot of time and money saved. We'll illustrate the process with the dual Xeon socket server design we see here. How does hyperlinks allow you to verify all of your serial links? By automating the entire extraction and analysis process front to back. You identify the nets of interest and the serial link protocol you're using, and Hyperlinks does the rest. Hyperlinks does all the topology extraction and modeling automatically, allowing you to trade off accuracy for turnaround time. 2D via modeling is lightning fast, and the 3D cut and stitch flow is fully automated. In order for the cut and stitch methodology to be valid, the signal needs to be in TEM mode at the signal ports, and the majority of the signal's return path should be contained within the area. Here, we see an animation of VIA behavior for our design at the Nyquist frequency, showing both signal and return current. You can see the return current is well contained within the area, and therefore the methodology assumptions are valid. The 336 channels on the design we showed earlier will produce hundreds of critical areas that need to run in the full wave solver. Running all those jobs one after the other will take too long. Hyperlinks lets us scale solver performance by running jobs in parallel. Hyperlinks actually allows two forms of acceleration. We can add more cores to each job to make it run faster, and we can run jobs in parallel to make the total process run faster. Hyperlink's job distribution supports a number of different distributed computing architectures, so you can configure the process based on the resources you have. Hyperlink's job distribution makes it possible to front end large simulation jobs with an ordinary laptop. Here, a laptop in Siemens, Massachusetts office is used to run solver jobs in the Oregon Siemens office. A total of 660 jobs were run, 30 at a time, using a total of 480 physical CPU cores. All the jobs were completed in 20.5 hours with 92% efficiency, meaning just 8% of the time was spent on computing and communication overhead. That's with everything running remotely across the country. This means that you can adjust the solver performance to meet your turnaround needs. IBIS AMI models represent a specific vendor's actual silicon and are the most accurate way to predict serial link behavior. That said, they're also the most expertise and time consuming analysis that we can do. That's why it's important to take as many problems off the table as we can before we start running IBIS AMI simulations. If we're finding basic problems with IBIS AMI models, we're wasting our time. One added benefit by using the progressive verification methodology, by the time we get to IBIS AMI simulation, the tough channel modeling work is already complete. The CerDes analysis reports Hyperlinks produces are HTML based and organized into different sections with links between them. Results are colored green to indicate a passing result, with red indicating a failing result. You can see your design's operating margins clearly and easily and share the report with colleagues. The compliance analysis report contains sections for overall operating margin, recommended equalization settings, crosstalk, frequency and time domain channel data, eye diagrams, and the design parameters used for analysis. You can save these reports in EDM, Siemens Enterprise Data Management Tool, and then share them with others over the web using EDM Collaborate. Hyperlinks workshops get you up and running quickly by documenting complete workflows with detailed step by step instructions and videos. Hyperlinks workshops guide you through the process with working examples so that you can hit the ground running on your own design simulations. Hyperlinks workshops like this one can be downloaded from the Support Center by following the Learn and Explore link from Hyperlinks area and selecting workshops. You can see a list of the different workshops on the right of the screen. In this presentation, we've overviewed the complete integrated flow Hyperlinks offers for serial link design and verification for the post layout. For the full flow, there's a pre layout schematic based topology exploration to develop placement and routing rules using progressive accuracy and standards compliance analysis, methodology for PDN design and verification for both DC drop and AC decoupling analysis behavior, how swept parameter analysis can be used to improve design margins, how we use Hyperlink's Design Space Explorer that can be used to explore and optimize designs with very large design spaces, such as complex vias, how hyperlinks can ensure your design meets standard protocol requirements using automated compliance analysis, and how hyperlinks' post layout progressive verification methodology finds as many problems as possible, as quickly as possible, with as little effort as possible. Automated post route extraction and modeling that lets you verify the behavior of all your signals, not just a select few. Comprehensive HTML based reports that tell you what you want to know most, what passed and what failed, by how much.